Hello everyone, and welcome to an online training video from Academy of Sound Engineering. This video is for the first year Digital Audio Theory course, which has a course code 5DigAud. I'll use my Digital Audio Workstation Technology book as if it were a theory class with the pages from my book on the projector screen. Today I'll cover the first 6 pages of Chapter 7, from page 193 to 199. In this section of the book, we look at the disadvantages of analog audio as well as the advantages of digital audio. Let's start with the disadvantages of analog audio. Firstly, analog audio is continuous. This means that it's infinitely changing. Point number 2, because it's continuous, there are no rules. Because there are no rules, analog audio cannot tell the difference between wanted noise and distortion or unwanted noise and distortion. It accepts all signals, whether we want them or not. With analog audio, anything goes. Point number 4, every time analog audio changes from one medium to another, a little bit of noise and distortion is added to the signal. And point number 5, lastly, with analog audio, the waveform is everything. If the wave shape is damaged in any way, we will hear it. Now let's look at the advantages of digital audio. Firstly, digital audio is discrete or fixed. Because it's discrete, there are very fixed rules. Because there are rules, it's very easy to tell the difference between wanted audio and unwanted audio. Point number 4, with digital audio, it doesn't matter how many times the signal changes medium. As long as it stays digital, there will be no loss in signal quality. And lastly, with digital audio, the waveform is irrelevant. Let's illustrate this using images from my book. On page 194, there's a picture of an analog sine wave. The sine wave is plotted on 2 axes, amplitude and time. On page 195, we see a clipped analog waveform. What's happened is the amplitude can't go above 4 volts in this case. If the waveform tries to go above that voltage, it just gets chopped off at the top and at the bottom. It's a clipped waveform. This is known as distortion, or fuzz, or clipping. Moving down to page 196, here's a noisy analog sine wave. Once again, the analog waveform has changed. With analog, the waveform is everything, so we'll hear that noise. On the next page, here's an image of a digital waveform, with ones and noughts to represent the on and the off states of a switch. If we move down to the next page, we can see a noisy digital waveform. Because there's such a huge difference between a 1 and a naught, a 1 represents full voltage positive, and a naught represents full voltage negative, as long as we can still tell the difference between a 1 and a naught, the noise is simply ignored. Here is a clipped digital waveform. The top and the bottom has been chopped off. But once again, it doesn't matter. We can still tell the difference between a 1 and a naught, even though it's distorted. So what's the difference between wanted noise and distortion and unwanted noise and distortion? Well, there are plenty of examples of useful noise. Cymbals and hi-hats are noisy sounds used to make music. A snare drum is mostly noise. Many sound effects, such as a waterfall or wind or an explosion, are based on noise. Unwanted noise is often called hiss, and all analog equipment, such as mixing desks, amplifiers, and tape machines, generate a small amount of it. Analog systems don't know the difference between a recorded cymbal sound and the hiss caused by the equipment. The hiss becomes part of the waveform. The wave shape has changed, and this change is audible. An example of wanted distortion is an overdriven guitar amplifier, or a fuzz pedal to create a similar effect. The sound of distortion is used by many rock, blues, and heavy metal guitarists. Unwanted distortion is when an analog signal accidentally overloads or clips the circuits in the equipment. Digital audio doesn't care about the shape of the waveform. It only cares about counting the numbers. This is how digital audio is able to separate out wanted signals from any unwanted noise or distortion. Please read through pages 193 to 199 of my book, because there'll be a pop quiz on LMS this week to assess your understanding of this content. See you next time.